To this ever-diminishing audience, I ask if there are any questions about the last lecture. Yes, sir.
Could you say which of the results we've gotten depend upon field theory, and which of those can be gotten just using SU3 without field theory?
Every result we have, well, of course, implicit is quantum electrodynamics as a field theory, in saying that the electrodynamic interaction can be characterized by two form factors. That's, in a sense, a field theoretic statement, right? Because what we actually measure, nobody has ever measured a virtual photon scattering off of a proton. What we have measured is electron scattering off of protons, and from our external magnetic fields affecting protons, and from that we deduce something about the virtual photon-proton vertex. That's an intrinsically field theoretic concept. On the other hand, from that point on, the fact that the scale of the 8 baryons are created from the vacuum by the action of local fields, etc., all the field theoretic apparatus and the ideas of renormalizability in particular play no role. It's a pure symmetry argument. Okay. And of course, if I derived, which I have not done in these lectures because they're rather boring predictions and hard to check, relationships among cross sections or strong interaction decay amplitudes for highly excited states, coming from SU3, that would involve no field theory at all. Someone who didn't believe, well, the essential thing in what is field theory? The essential thing is probably the idea of local observables, as stressed in the first semester. And then the other essential ingredient that in the apparatus is renormalizable perturbation theory. Certainly renormalizable perturbation theory plays no role, and even local observables play no role. You could imagine a theory without local observables in which you could nevertheless, by some other route than we chose, define an S matrix. And then if that theory were SU3 invariant, the S matrix would obey some rules derived from SU3. So there's very little field theory in that. And the things I'm going to talk about this lecture, the Gelmano-Kubo formula will again be a field theory-free formula. And when I discuss the electromagnetic decays of vector mesons, which is connected with the GMO formula, it's an independent check of a part of it, that will involve a bit of field theory because we'll have to use field theory again for the electromagnetism, although not for the strong interactions. Okay? Why did you ask that question? Just curious? Or, I mean, was it an implicit criticism? What are these lectures doing in a course on field theory? It's a course on relativistic quantum mechanics. And are there other questions? Well, we talked about a world in which we had perfect SU3 symmetry, last lecture, in which we had perfect SU3 symmetry, except it was broken by the effects of electromagnetism, which we treated perturbatively. The mysterious medium-strong interactions, those interactions of greater than electromagnetic strength, which break SU3 symmetry, were ignored. Now, in this lecture, I'd like to turn to the medium-strong interactions and do the same thing, treat them, ignore electromagnetism, and treat them as a perturbative effect upon the strong interactions. We have to start from further back. Because although by hypothesis we know the Hamiltonian for the strong interaction world is a sum of the very strong part and the medium strong part, where this is SU3 symmetric and this is SU3 breaking, we don't know nearly as much about the medium-strong interactions as we do about electromagnetism. Electromagnetism we knew was mediated by a photon. We had the condition of renormalizability that selected out minimal coupling that enabled us to tell us that the current transformed the same way as the charges, etc. We have no such handle here. And if we're to make any progress along the same lines, we would have to make guesses, either about the dynamical theory of the medium-strong interactions or about the output of such a dynamical theory insofar as pure symmetry computations go, how the medium-strong interactions transform under the SU3 symmetry group. Such a venture is not a priori guaranteed to be successful. It's possible that SU3 is a good symmetry of nature, but the medium-strong interactions are very complicated, and under their symmetry transformation properties have sums with more or less equal weights of pieces that transform like every conceivable representation of the group SU3, in which case we would get no sum rules, analogous to our electromagnetic one. However, it turns out a posteriori that the simplest guess, which anyone constructing such a theory, and in particular Gell-Mann, was tempted to make, that the medium-strong interactions have simple transformation properties under SU3, turns out to fit experiment very well. Gell-Mann's guess HMS transforms under SU3 like a member of 1,1, the octet representation. Of course, what member it is uniquely determined by the fact that the medium-strong interactions preserve isospin and hypercharge. It must be the I equals 0, Y equals 0 member of an octet of operators, the lambda-like member, if you will. As I stress, once again, this is pure hypothesis. If it didn't work, it wouldn't mean SU3 was wrong. Then you would try the next thing. Maybe it transforms like a 2-2, or a sum of a 1-1 and a 2-2. However, certainly the simplest guess you can make is among those things that would give Baryon mass differences to lowest order in perturbation theory, and therefore it is a thing to try. Of course, if it works, it is evidence for both Gell-Mann's guess and the general idea of SU3 symmetry. We're going to use this hypothesis to compute medium-strong mass differences within SU3 supermultiplets using ordinary perturbation theory. Except there's a little finagle traditionally used. It's not really that important. We compute delta M for fermions, but we compute the shift in mu squared for bosons. This is inspired, of course, in the strict sense of lowest order perturbation theory. It doesn't matter, because delta mu squared is 2 mu delta mu, and therefore if splittings were really small, it wouldn't matter if we obtained linear relationships for the shifts in mu squared or the shifts in mu. The splittings are not really that small, and there seems to be some small improvement obtained by using the rule of using delta mu squared for bosons. Was a guess. All I can say historically is that it was done, the guess was made before the eta was discovered by a couple of weeks. So it wasn't a guess made after the fact, it was a guess made before the fact. And of course, it's inspired by field theoretic ideas in which you think of corrections to the self-energy operator of a fermion making a shift in the mass, and corrections to the self-energy operator of a boson making a shift in the mass squared. Now, an amusing thing about this thing is that once you've made this hypothesis, you can in fact write down the formulas for the mass shifts within an SU3 supermultiplet in a closed form for a general supermultiplet. You don't have to tediously multiply matrices and tensors for any multiplet. In order to do that, I will first count how many unknown constants there are for the masses within any given multiplet, and then construct operators which will enable us to construct, and then I'll go on. I can't construct a sentence at the moment, although I will construct an operator shortly. Our task is to find out how many times nm times this complex conjugate, mn, contains 1, 1. because that will tell us how many ways there are of coupling an octet to a psi bar and a psi, and therefore how many terms there will be in our mass formula. I will prove to you that it contains 1, 1 twice if neither n nor m is 0. Sorry, n not equal to 0, m not equal to... Oh, there's an easy way of saying that. nm not equal to 0. Once, if nm equals 0, that is to say either n or m is 0, but one of them is non-zero, and of course not at all in the trivial case. The proof can go directly from our algorithm for the reduction of a direct product, but in fact it can also be shown directly by manipulating tensors. Suppose I have some tensor representing traceless symmetric tensor representing an object that transforms according to the representation nm. I have its conjugate object here. I want to sum up indices in such a way that I'm left with an octet, that is to say a traceless symmetric tensor with one upper index and one lower index. There are obviously only two ways I can do it in general without using the epsilon tensor. I will come back later to the ways using the epsilon tensor. I can sum all of these indices with all of these, and all but one of these with all but one of these, leaving one index, one upper index here and one lower index here unsummed. That's one possibility. Then I can take out the trace to make an octet. I can't sum any of these with any of these because that's 0. I've got to sum them with these up here. Alternatively, I could pick the lower and the upper from the other set. Those are the two ways of making an octet. Using the epsilon tensor does me no good in this case. If I use one epsilon tensor only, I have 3 times more total lower indices than I have upper indices, or vice versa. And there's no way of summing to be left with one upper index and one lower index. And if I use 2 epsilon tensors, that's the same as a string of 6 deltas, of 6 differences of 3 deltas in various permutations, and therefore the same as the original thing we explored. Thus, there are only 2 ways of doing it, at most. And of course, if I have only upper indices on one side and only lower indices on the other, one of the possibilities is not a possibility at all. Now, therefore, if I can construct 2 operators such that in any representation they are octets, or equivalently, octets plus singlets, because a little additional singlet term is not going to bother me. That'll be absorbed in the overall mass that's there before I turn on the medium-strong interactions. I will have said the mass splitting is proportional to the matrix elements of those operators. I will now construct 2 such operators. One of them is trivial. Remember our generator matrix. I minus, I plus, IZ minus y over 2, minus IZ minus y over 2, y, and strangeness changing generators I'm not going to care about. This is an object that transforms like a octet. It is a traceless symmetric matrix, G, and therefore in particular one operator whose matrix elements would be equivalent to the, would follow the octet rule would be G33, which is y. This reasoning, I should have said this, I'm sorry, I forgot. This reasoning, for those of you who are not following it, is similar to the reasoning that leads to the establishment of the Wigner-Eckart theorem, where you say the matrix elements of every vector operator is proportional to the matrix elements of the angular momentum. There the reasoning goes, there's only one way to couple isospin 1 to a representation times its conjugate. Therefore, the same Clebsch-Gordon coefficients must occur in the matrix elements of the total angular momentum as occur in the matrix elements of the operator we are studying, and therefore the two are proportional. Likewise here, there are two possible independent Clebsch-Gordon coefficients, so I need to find two possible octet operators, and I have found one of them. I will now find another. Given any matrix, its cofactor matrix is also a matrix. The cofactor matrix is the matrix made up of, for those of you who've forgotten your elementary matrix theory in high school, is the matrix made up of the determinants of the minors that enters into the expression for the inverse. Cofactor A, Ij. Well, I should have made them one upper and one lower, is epsilon IKL, epsilon JRS. And since these matrices have operators, I'd better take the symmetric combination ARK ASL. That's obviously an object that transforms like a matrix. If A transforms like a matrix, that is to say like a combination of octet and singlet, since it's not necessarily traceless. Therefore, I will construct cofactor G 3, 3. This 3 should have been upstairs also. That is to say, the determinant of the minor on the 3, 3 thing. Well, that's pretty obvious. There I've got minus I minus I plus. I'm supposed to symmetrize the whole thing. Plus minus y over 2 minus IZ minus y over 2 plus IZ equals, aside from a factor of 2, y squared over 4 minus total isospin squared. Thus, that is our second operator, which transforms like the 3, 3 element of an octet. And we have the Gelman-Okubo mass formula. The original proposal was by Gelman. He worked out the Clebsch-Gordon re only for the octet, and then Okubo showed, by a different argument than the one I have given, how to write it for any representation. M for fermions, mu squared for bosons, equals a additive constant, that is the mass present before the medium-strong interactions are turned on, plus a second constant times the hypercharge, plus a third constant times, as it is usually written, I plus 1 minus y squared over 4. Are there any questions about the derivation of this formula? Of course, I should say that in the case of representations for which either n or m is 0, these two things must turn out to be linearly proportional to each other, or else we've made a mistake. I leave it as an exercise for you for showing that the representations for which n or m is 0 have the property that indeed I times I plus 1 minus y squared over 4 is always proportional to y. Any questions about the derivation of the formula? It's a cute argument. It's due to a Russian called Smorodinsky, who I don't think works in high-energy physics. He showed it to me at the Dubna conference 12 years ago. It's a nice way of getting the operators.
So why are you using the 3 elements of 3?
Because those are the only ones with I equals 0, y equals 0. All the others carry isospin or hypercharge. Is that you looking blank? Is that, or is that just your normal blank expression, or is so you're not satisfied? We're not satisfied with that answer.
Yeah, I'm satisfied with the answer.
Okay. Now, let's go and apply this to. We know a lot of things. We know there are a lot of complete SU3 representations around where all the particles have been discovered. So let's begin with the famous one, the Baryon octet. The octet with j to the p equals 1/2 plus. That's composed of the nucleon, for whom this mass is A plus B plus 1/2 C by this formula. Did I do that right? Hypercharge 1, I equals 1/2. 3/4 minus 1/4 is indeed 1/2. I did it right. The cascade, which is the same thing except the hypercharge changes sign. The lambda, which is pure A. The sigma, which has 0 hypercharge and isospin 1. So this is plus 2C. Therefore, we obtain the formula originally written down by Gelman. I will, in order to avoid infesting the board with M's, I will denote the masses of the particles by their names. Nucleon plus cascade, that gets rid of the B term and gives me a C term, equals a 1/2 sigma plus 3 lambda. That cancels out the A and the C on both sides. Thus, we obtain one relationship among these masses. Is there any question about the derivation? Now, what about experiment? Well, I've had the Rosenfeld tables, most recent edition, and my little Hewlett-Packard machine, but I don't seem to have page 2 of my notes, which will be embarrassing. There it is. So I worked it out. I used, of course, we expect the accuracy of this formula. The things we are neglecting are second order and the medium-strong interactions. And although the medium-strong interactions are medium-strong, even second order in them is larger than electromagnetism. So I didn't bother to take account of the electromagnetic mass shifts within the multiplets. I just took the mean average over all of the mean average. I just averaged over all the electromagnetic masses. 939 plus 1318. This is an MEV. And of course, the errors in these masses are negligible compared to the expected error in the formula. 1192 plus 3 times 115 over 2. And unless there was an error in my chip, this is 2257, and this is 2268, which is pretty good. Indeed, better than we would expect. Even the most violent enthusiast for SU3 must say this amount of agreement is just fortuitous, because for heaven's sake, the error is less than a typical is on the order of a typical electromagnetic mass splitting, and you don't expect it to be that good. Next one along, going along through the well-known fermions, is the there is, of course, as I told you in my isospin lecture, J sub p equals 3/2 plus resonance in pion nucleon scattering. In a perfectly SU3 symmetric world, that must be some resonance that occurs in meson baryon scattering. That is something that occurs, part of some representation that occurs in the direct product of 8 cross 8. 8 cross 8 equals 1 plus 8 plus 8 plus 10 plus 10 bar plus 27. Now, if all we knew about was the delta, the I equals 3/2 y equals 1, we could still say that there were only a small number of possibilities here, because it certainly can't be in a singlet, because that doesn't contain the object with I equal 3/2, nor in the 2 octets. It can't be in the 10 bar, because that contains an object with I equal 3/2, but it has hypercharge -1, not +1. So the only possibility would be it is either part of a set of 10 or part of a set of 27. In the early days of SU3, before things were worked out, some people thought it was in a 27. Glashow and Sakurai wrote a long paper called The 27-Fold Way, in which they gave a variety of convincing arguments why it should be part of a 27. But it turned out, in fact, to be part of a 10. Its relevant energy range at all possible hypercharge channels has been extensively explored, and there are none of the other objects that would be there in a 27, just the things that would be there in a 10. And it will write down the elements, yes?
Could you explain why it can't be the 1 and the 8 range?
Because it has I equal 3/2. It can't be part of an octet if it has I equal 3/2, because there's just I equals 1, 1/2, and 0. Using the reformed Rosenfeld names for baryon resonances, in which instead of giving them individual names like Y star and K star like we used to, you name them according to their isospin and hypercharge. The decouplet consists of I, Y, 3/2, 1, that's our old friend the N star, which is a delta, whose mass is now put at 1232, but it's a rather broad bump, so where you put the mass is a matter of taste. And then the other ones get narrower. I equals 1, Y equals 0, something that is called the sigma 1385. Those are all in MEV. It's named after the familiar particle with the same isospin and hypercharge. 1/2 minus 1, an excited state of the cascade, 1534. And the famous omega minus 0 minus 2, the completion of the decouplet, with 1672. There's the famous incident at the International Conference. This had been known, this had been discovered, this was announced at the conference. Gell-Mann looked at it and said, that's a decouplet, I predict lots. We will see how well he predicts it, because, of course, it's very simple. For the case of this is a representation 3-0, and therefore these two terms are proportional, as you can check. Or equivalently, we can just look at one of them that says the mass splitting is proportional to the hypercharge difference, i.e. the differences should be the same as we go along this line and the hypercharges go up. Well, it's easy to compute the differences. Thus we have two predictions, unlike the one we had for the baryon octet. Once we know one of the differences, we predict the other two. The differences are 153, 149, and 138, which is, again, very good, considering that we are only going to lowest order in the medium strong interactions. We notice there seems to be a trend, but it's usually dangerous policy to attempt to deduce deep physics from something like that. Are there any questions about the derivation of the formula or its application in this case? Okay. Another blackboard, another application. Shortly, this one will also work, then we'll come to one that doesn't work, and there's interesting history attached to that. J sub p equals 0 minus, the pseudoscalar octet. In this case, we can just copy down the baryon formula, except now the masses, of course, will be mass squareds because they're bosons, but I'll still use the name. The analog of both the nucleon and the cascade is the kaon. So I obtain twice the mass squared of the kaon, equals 3 eta plus the mass squared of the pi, effectively 0, over 2. And I will write it in the form that it was first written as a prediction of the eta mass squared. Let me look at my sheet, it's a trivial algebra. Eta mass squared equals 4/3 k minus 1/3 pi. Or to get the formula in the shape where you can sort of see where the eta should be, k plus 1/3 k minus pi. That is to say, it should be a little bit heavier than the kaon, which of course it is. Here I'll write down the mass squareds in BeV squared. The eta mass is 0.301. It should equal 0.246 plus 1/3 0.227. As you see, the pion mass squared is zilch compared to the kaon and the eta mass, or 0.322, again, unless I've suffered from chip failure. Again, this is a better agreement with experiment than we would expect, not the typical 20% error, but a 10% error or less. This is really surprising because the pion mass is so far out of the of line with the other masses that it's amazing the formula works at all. Indeed, one of the reasons people spent 4 years exploring the dead end of global symmetry, which I talked about 2 weeks ago, was that global symmetry, because it was a product of SU2s, enabled you to put the pions in a representation all by themselves. I think in the notation I gave the representation 0, 1, 0 of the product of those 3 SU2s. And therefore, since everyone said, well, obviously, although the 8 baryons must be part of a multiplet, the pions and the kaons are so different in mass, a very important constraint is that we should be able to put the pions in a multiplet all by themselves. It's just too preposterous to imagine there is a symmetry which puts the pions and the kaons together. They look too different. I also remember, with pain at the time and delight in retrospect, when Glashow and I published our electromagnetic mass formula, there was a physical review letter by Sakurai, who had a different theory of electromagnetic masses, in which it contained the scathing footnote, formulas in the SU3 symmetry scheme have recently been derived by Coleman of Glashow. The reader should understand that these formulas are valid only in the approximation mk squared over m pi squared equals 10 equals 1. That was a well-taken criticism, but it turns out it works all the same. Yes, yes, Kay. Oh, but that is a representation 3-0. It turns out to be the decouplet that wins. So this term is proportional to this term. There is only one thing if either n or m is 0, as you can check by direct algebra if you want. And therefore, the mass splittings are linearly proportional to the hypercharge, and therefore the successive differences should be the same, since the hypercharge goes up by 1. And now we continue Gaffer Coleman's reminiscences. Hey, let me tell you about the great days of SU3. And go on to the next obvious octet that was also being discovered in those golden days of 1961, the vector mesons. The rho had just been discovered. Those of you who think of the rho as a permanent part of our universe should remember there was a period when the original Rosenfeld data card contained a subtable labeled resonances that had one entry on it. There was a time when the rho was a great discovery, and it was followed rather shortly by the omega and the phi in January of 1961, as I recall. And they were obviously an octet. And although that turned out to be a bit wrong, therefore for reasons I'll explain if I get to number 3, and therefore you have the corresponding formula for those things. Octet consisting of omega with I equals 0, y equals 0, rho, an isovector, and the k star is the same quantum numbers as the k, except being a vector particle. And you get the corresponding formula, omega equals k star plus 1/3 k star minus rho. The data here is 0.613 is the mass squared of the omega, and BeV squared equals 0.796. You can already see I'm heading for disaster because I'm going to add a positive number to that. Plus 1/3 0.203 equals 0.864. This is not good. Especially when compared with the sort of results we have up here. Well, Murray Gell-Mann was not a man to give up an idea lightly, and he said at that time, well, the reason for this, we can think of a mechanism that does this. Let's suppose that just by chance, by something to do with the very strong interactions, which we don't pretend to understand, in the absence of SU3 breaking, there happens to be a vector SU3 singlet very close in mass to the degenerate vector octet. This is what you would compute. Sorry, not this. 0.864. Would be the mass of the octet if the singlet weren't around. But because the singlet is around, things are going to be different. Let's focus attention on the subset of the world, of the big Hilbert space of the world, which is a two-dimensional Hilbert space spanned by a state of the singlet vector meson, omega 1, and this hypothetical octet vector meson, omega 8. And I'll write down the 2x2 matrix, mass squared matrix, for that in this basis. Now, Gell-Mann said the omega 1, of course, will acquire some mass, both because it has a mass in the absence of the medium-strong interactions, and medium-strong interactions may give us some correction, so we'll have an m1 squared here. The omega 8 will acquire a mass, which we've just computed. But an octet operator can not only connect octet with octet, it can connect octet with singlet. And therefore, exactly the same interaction that makes this thing here and this thing here could put in a cross term, which I'll call x, some quantity. X is the same order of magnitude. The off-diagonal matrix element should be on the same order of magnitude as the diagonal matrix elements. Therefore, if these masses were very widely separated by, say, 500 or 600 BeV, and this thing were on the order of the sort of splitting BeV, 0.600 BeV squared, if these sorts of things were, if this matrix element was on the order of the ones we've been computing, a couple of hundred, around the 10th of a BeV squared, then the effects would be negligible of this off-diagonal term, as we know from lowest order perturbation theory. On the other hand, if by some fluke these masses happen to be fairly close together, then we know this off-diagonal term can have a very large effect. If we have two nearly degenerate energy levels in atomic physics, and we introduce a mixing matrix element, a symmetry-breaking Hamiltonian that connects the two, then one of them is pushed up and the other one is pushed down, and the amount of pushing can be comparable to the size of the mixing matrix element. That is to say, 0.200 or so on the scale in which we are working. Therefore, he hypothesized there was this situation going on here. It was an instance of nearly degenerate perturbation theory, and therefore the omega 8 and the omega 1 was one pushed up and the other pushed down. Here we see something lower than the predicted result. Therefore, the other one is the one that's pushed up. And of course, you can't determine the exact amount of pushing up unless you know m1 squared as well as m8 squared. But you can say there must be an isosinglet, Jp equals 1 minus meson, with a mass somewhere between 100 in the scale between 0.1 and 0.2 times greater than 864. That was his prediction, not a precise numerical prediction, but there should be such a particle around. Among the graduate students of Caltech at this period, this particle was known as the fudgon. And we were uniformly surprised when the phi was discovered, which had exactly the predicted properties. And the mass squared of the phi is 1.004 in the right ballpark. This is, of course, not a qualitative prediction. It could differ by 10% one way or the other and it'd still be okay. Not a quantitative prediction, I should have said. Are there questions about the sort of physics that is going on here? Now, you might say there is no predictive power other than a qualitative one in this scheme because we don't have a precise numerical prediction. We have, for this subsystem, 3 unknown quantities, m1 squared, m8 squared, and x. Oh, I should have said, why did I write x here rather than x star? Because the phase between omega 1 and omega 8 is at my disposal, so I can make this matrix element real. I have 3 unknown quantities. One of them I know from the GMO formula, m8 squared. I don't know a priori m1 squared and x. I have 2 experimental numbers, the mass of the omega and the mass of the phi. And therefore, if I want to, I could deduce m1 squared and x, but that's hardly a prediction since you can't go to God and say, what values did you assign for m1 squared and x to check it? However, I can predict the so-called mixing angle, and it turns out that that is, in a sense, experimentally measurable. I will first go through the prediction of the computation of the mixing angle, and then tell you how you measure it experimentally. The mixing angle is the angle that tells you how much of the physical omega is omega 1, omega 8, and how much of the physical phi is omega 1 and omega 8. If we stick to this 2-dimensional Hilbert space consisting of a omega and a phi at rest, spin degrees of freedom suppressed, of course, we would diagonalize this matrix, and the actual eigenstates of m squared, the actual physical particles, would be the eigenvalues of this matrix, conventional neurodegenerate perturbation theory. Thus, since this matrix is real, its eigenvectors must be real combinations of omega 1 and omega 8, and therefore I can define a phi, which is cosine theta. Theta, this is the definition of the angle theta. Omega 8. Turns out the phi is mainly omega 8, so that's why I defined it that way. Plus sine theta omega 1. And the physical omega must be the other eigenvalue, that is to say the orthogonal combination, cosine theta omega 1 minus sine theta omega 8. That's conventional perturbation theory. Now, I can determine the angle theta in terms of physically observable quantities, in terms of the masses. I could, of course, do it by finding m1 squared and x from this formula, but I can do it much more directly. I observe that m squared 2, I observe any matrix can be written in terms of its eigenvectors and eigenvalues. So m squared is m phi squared phi phi, 2 by 2 vectors, plus m omega squared omega omega. Omega 8, m squared omega 8, is the quantity we have called m8 squared, the number we computed from the GMO formula before we put in the existence of omega 1, which is equal to, take m phi squared cosine squared theta, dead wrong, sine squared theta plus m omega squared. No, dead right. The phi is, what am I doing? Cosine squared theta plus m omega squared sine squared theta, from which it is a work of a moment to compute sine squared theta. And since I'm going through such agonies of writing things down wrong, let me just check it. This is m omega squared minus m phi squared sine squared theta plus m phi squared, using the famous formula cosine squared theta is 1 minus sine squared theta, or sine squared theta equals m phi squared minus mh squared over m phi squared minus m omega squared, equals, by some elementary algebra from numbers already put on the board, 0.36, or cosine squared theta, which we'll also need later, by some even more elementary algebras, 0.64. We see theta is closer to 1 than it is closer to 0 than it is to 90 degrees, so I put my convention in right. According to this, the phi is mainly omega 8, and the omega is mainly omega 1. Are there any questions about this derivation? There may be a question about what good is this number. I will explain what good this number is in a moment. The questions? No. Okay. Now the application. The application of this mixing theory, which we have developed, is to leptonic decays of the vector mesons. Omega, rho, and phi decay not very much, but they do into E plus, E minus. We understand electromagnetism very well, so we know the kind of diagram that is responsible for this process. A vector meson, omega, rho, or phi, goes along. There is a mysterious strong interaction blob about which we can say nothing. A photon comes out, because that's the only way you'll make an E plus, E minus pair, virtual photon, and decays into an E plus, E minus pair. Thus, this thing is proportional to the matrix element between the vacuum and one vector meson of the electromagnetic current, because once we peel off the electron-positron pair, that's what's left. This is a very simple example of a one virtual photon process in which we have to take the matrix element of an octet operator between an octet state, if this is an octet vector meson, or a singlet state, if it is a singlet vector meson. In the case of singlet states, of course, an octet operator cannot, in the limit of strict SU3 symmetry, connect a singlet operator, a singlet state, to a singlet state. Both the vector meson and the vacuum are SU3 singlets, and therefore the amplitude in the SU3 symmetric world, in which the eigenstates are omega 1 and omega 8, because I did it for minimal coupling, and the success of the formulas for magnetic moments that were all based on the assumption that it was pure octet. It's I sub z plus y over 2. And both I sub z and y are generators of SU3, i.e. elements of an octet with no singlet admixture. Is that a satisfactory answer? You could say maybe there's some other quantum number, charm or whatever the opposite of charm is, obnoxiousness, that happens to be 0 for all observed particles, is not one of the SU3 generators, and contributes to the electromagnetic current. Maybe there is or maybe there ain't. However, it doesn't, even if there is one, it doesn't seem to have a strong effect on the electromagnetic properties of the baryons, because otherwise our magnetic moment formulas would be badly off, since that would introduce a third constant into our formula for the magnetic moments, the matrix element of the singlet operator. Okay, so if it's there, it doesn't have much of an effect on the baryon magnetic moments, so it probably won't have much of an effect on vector meson decays. It may have an effect on some very heavy particles where the dynamics of charm or obnoxiousness are important. I'll call V for vector meson. Amplitude should be proportional to the matrix element of the electromagnetic current, that is to say, by our earlier tricks, trace V epsilon, where epsilon was the 3×3 matrix that entered the expression for the electromagnetic current. I remind you, epsilon is 1/3 2 -1 -1 zeros everywhere else. Of course, this is trivially 0 for other than the two neutral members of the octet, omega 8 and rho naught. Let us compute it, however, for omega 8 and rho naught. For omega 8, that's a lambda-like object, so the matrix V is square root minus square root of 1/6 minus square root of 1/6 twice the square root of 1/6, zeros everywhere else. Trace of V epsilon equals 1/3 minus 1, well, square root of 1/6 is, of course, a common factor. 2 minus 2, off to a great start, plus 1. 2 times minus 1 is minus 2, equals minus square root of 1/6. For the rho, that's a pi naught-like object. I should really say the rho naught. V is, of course, the rho plus and rho minus do not decay into E plus E minus pairs. That is square root of 1/2 minus square root of 1/2, 0, 0, 0, 0, 0, 0, 0. Trace V epsilon is 1/3 square root of 1/2, a common factor. 2 plus 1 equals square root of 1/2. Thus, amplitude rho goes into E plus E minus equals √3 amplitude omega 8 goes into E plus E minus. This is how the world would be in perfect SU3 symmetry. There would be a rho, an omega 8, and an omega 1. The omega 1 would not decay into E plus E minus at all. The omega 8 would decay into E plus E minus, and the rho would decay into E plus E minus 3 times faster because the decay rate is the square of the amplitude. In the real world, there is not perfect SU3 symmetry, and in this case, because there is a mixing effect, the mixing effect, when there are effects caused by presence of small energy denominators, are much larger than other effects of symmetry breaking violations. And therefore, we must take account of the fact that the real eigenstates are not omega 1 and omega 8, but phi and rho. Thus we find, taking account only of the mixing effect, and not of the other effects of SU3 symmetry breaking, because they're supposed to be small. That one is anomalously large. No, because omega 1 and omega 8 are close in mass. Taking account of mixing only, gamma phi into E plus E minus over gamma rho naught into E plus E minus. The phi is omega 8 with an amplitude cosine theta, so that gives us cosine squared theta over 3, because there's of this root 3 in here. Equals 0.21 theory. Gamma omega into E plus E minus, which is rather badly known experimentally, into gamma rho naught into E plus E minus, is sine squared theta over 3 is 0.12, theoretically. I have not taken any account of phase space. We are not close to a threshold. The E plus E minus threshold is very low compared to phi and rho. So phase space correction factors will be on the order of other effects of the medium-strong interactions, which we are systematically neglecting. So why retain them when we are neglecting all the others?
Say the same thing about putting a mass of the meson into the photon propagator?
Yeah, the whole story. I don't care what power of the mass it goes by. In fact, you can make a convincing argument that the upshot of all of that, the upshot of the whole thing is that the matrix element is proportional, the decay rate is proportional linearly to the mass. And that'll multiply, if I were to put that in, it would multiply these predictions by 20 or 30%, but that's the kind of error I am making by throwing away all except the mixing effects of the medium-strong interactions. You want to put them in? You can put them in. In fact, it makes the predictions worse, but that's not the reason I left them out. Cross my heart. I mean, it's a kind of cheating. It's only if the threshold is close to the, if the decay process is close to the threshold, then you would expect the effects of small mass difference to give you a large enhancement, and then it's reasonable to put them in. Now, the experimental numbers of these things are fairly well known, if I can find them. Yes, they are. For this one, the experiment, according to the latest Rosenfeld tables, is 0.20 with an error of around 15%. But if you put in the mass difference, if you put in the mass factors for phase space, you'd make it apparently worse. But you'd make the prediction 0.3 or something like that, a little less than 0.3. But so you shouldn't take the fact that it falls right in the middle to be too seriously, but that it falls in the right ballpark you should take very seriously. For this one, the experimental number happens to be, I didn't fudge it, 0.12, but the error is quite large. In fact, Rosenfeld says, I shouldn't say Rosenfeld, the particle data group says that they think the error should be twice the published standard deviation, and if you take them seriously, that's around a 40% error. As I say, the fact that these things are in the right ballpark is what is important. If, for example, I didn't have a lot of this is this 3 in the denominator. That's a pure SU3 Clebsch-Gordan coefficient. If I didn't have SU3, it would be as a priori plausible to put the 3 in the numerator as in the denominator, which would change my results by a factor of 9. And then they would be very different. Okay, so it is not a non-trivial result. It's not that, of course, qualitatively it comes out right. If I had the 3 in the denominator, this would be something like 2, and this would be something like 1, and it would be in the numerator instead. It would be grotesquely off. Okay. That concludes the applications, numerical applications, and the actual experimental checks I am going to make of SU3, although, of course, there are many others. The literature is chock-a-block with them. Notice we have done a lot more predictions in the last week than we've done throughout the entire remainder of this course. So just because this doesn't involve deep thoughts and field theoretic concepts that make your head feel funny, don't think this isn't a real thing. We've predicted with good accuracy 2 magnetic moments, 1 electromagnetic mass splitting, 1 baryon medium strong mass splitting, 2 decouplet medium strong mass splittings, 1 pseudoscalar meson medium strong mass splitting, and 2 ratios of electromagnetic decay rates, and they've all come out right. Okay. Now, the next... I beg your pardon? I didn't catch the joke. Now, in the remainder of this lecture, I'm going to talk about SU3 associated ideas. I'd like to say a few words, although I'm not going to make any predictions or do any numerical work about the famous quark model, which is a real rags to riches story. Started out as universally scorned and gradually accepted by even the most snooty of us. Although it's like all rags to riches novels, they of course sometimes are Dickensian rather than Horatio Alger in form. They may establish a trajectory. It may fall once more. But I would like to talk about the basic ideas of the naive quark model from the viewpoint of SU3 symmetry without talking about quark dynamics, which is a much more disputed subject. So the last half hour of this lecture will be much more looser and semi-popular in structure than what has gone before. And I'll give you a sort of historical outline and make comments occasionally about how SU3 ideas come in. First, I will discuss the naive quark model, and then I will make a few remarks at the end about what is called quantum chromodynamics. So you'll know what that means when you... It's another wonderful name from Caltech. Always something new out of Pasadena, as Pliny said. Okay. From the very first days of SU3, indeed even before the papers were written, people realized that there might be some physics in the group theoretical statement that all SU3 representations could be built out of 3s and 3 bars. In particular, there was something extremely attractive in the formula 1, 0 plus 0, 1 equals 1, 1 plus 0, 0. This is going to be a naive quark model. Or equivalently, 3 cross 3 bar equals 8 plus 1. They said maybe those triplets are not just mathematical figments. Maybe there really are particles that transform like SU3 triplets. Funny particles with charges minus 1/3 and minus 2/3, and likewise fractional strangenesses and so on. And that the real mesons and baryons, the octets, which we see around so much, are bound states of these triplets. And there was a wave when people would investigate alternative triplet models. They said, well, if you give the triplets some sort of nucleon number, then of course this octet and singlet is going to have nucleon number 0. It's particle and an antiparticle, and that's fine for the mesons. It's not so good for the baryons. And some people said, well, maybe you need another two kinds of triplets, one that carries nucleon number and one that doesn't, and then you'd make a baryon by binding together a nucleon number carrying triplet with a nucleon number non-carrying triplet. And some said, well, maybe you need a particle around that's a fundamental singlet that carries nucleon number, and you'd make a baryon by putting together three of these things. The big discovery, which was rather trivial, was, but important at the time, was made simultaneously by Gell-Mann and Zweig, who said, suppose you put together three 1-0s. Now, they said, let's work out what this is. Firstly, the first step, 1-0 cross 1-0 equals, by our algorithm, 1-1-0-0. No possibility of peeling things off the inner pair or the outer pair. So that goes down to 2-0, which is a six-dimensional representation, plus peeling a pair off here and adding 1 to here, 1-1, which is our old friend, no, 0-1, a 3-bar. Now, going on to the next stage, we already know what 0-1 cross 1-0 is, so we've got to compute 2-0 cross 1-0. Again, that's 2-1-0-0 with no further possibilities. That is 3-0 plus 1-1, the octet. Thus, the desired thing, 1-0 cross 1-0 cross 1-0 equals 3-0 plus 1-1, and then we've got to multiply 0-1 by 1-0, but we already have that, plus 1-1 plus 0-0. Or, in common language, three cross 3 equals 10 plus 8 plus 8 plus 1. And I haven't made any arithmetic errors, I hope. No, 27 is 10 plus 8 plus 8 plus 1. Now, this gets very intriguing if you take this idea seriously, because then if you say that there are fundamental objects called, I think, aces by Zweig, and quarks, the name that caught on by Gell-Mann. If you say there are fundamental objects called quarks, and things are made up of bound states of quarks, and if you say quarks have nucleon number 1/3, why not if they have charge 1/3 and hypercharge 1/3? Then we're in pretty good shape. Things begin to look a little less artificial, because you have two quark bound states and the quark anti-quark bound states, and they are supposed to be mesons, and they're octets and singlets. And sure enough, all the mesons that have ever been discovered are octets and singlets. And you've got three quark bound states, and they're octets and singlets and decouplets. And sure enough, they have all the objects with nucleon number 1. Of course, their antiparticles are three anti-quark bound states with nucleon number -1. And sure enough, those all go into octets and singlets and decouplets. No 27-plets or 35-plets or other exotic objects around. And no 10 bars with nucleon number 1, although, of course, there are 10 bars with nucleon number -1. They're antiparticles. So, looks somehow as if there's a glimmer of truth maybe in this idea. It seems to agree with the phenomenology of the observed hadron. On the other hand, it also looks sort of silly, because when you say a nucleus is made up of neutrons and protons, the way you establish that is not by studying nuclear structure. but by bashing a nucleus and watching neutrons and protons fly out. And of course, at that time, and indeed 10 years later, no one has ever observed a quark. No matter how hard you hit a hadron, more hadrons fall out, mainly pions, not any quarks. Also, this is if the reason for that is that the quarks are very heavy. Since the hadrons are not very heavy, the quarks must be very tightly bound. Then it's an extreme relativistic system. The binding energy is comparable to the E equals mc squared energy of the quarks. And therefore, you would expect there would be a large probability for there being virtual quark-anti-quark pairs. And, why should it be 3 quarks, more than 5 quarks, more than 7 quarks, more than 10 quarks? If they've got all that energy around, why should it just look like a simple non-relativistic system? You'd expect the wave function to have a large amplitude for having all sorts of pairs in it. Also, what kind of force is it that can bind together a quark and an anti-quark and 3 quarks, but doesn't bind together 2 quarks? Why can't we have a 2-quark bound state? That would be, we've worked it out here, a sextuplet plus a 3-bar, particles with fractional charge, just as every bit as easy to see as a quark itself. Why aren't they around? So there was all this argument back and forth, okay, and nothing ever got anywhere. And there were those who believed in the quark model and those who didn't, and those who believed in it used essentially non-relativistic reasoning to work things out because they said, I don't care what the kinematics are, it looks non-relativistic. And the results were sort of good and sort of bad, and it was a big mess. It still is a big mess in many respects. It's just that we're beginning to get an inkling of how to incorporate these ideas into a relativistic quantum field theory. But that you must save for your post-253 studies. I'm just giving you an overview at this moment. Are there any questions at this stage? Why it's an attractive idea and why it's an unattractive idea? Yes?
Well, I think you can solve the business of that pair production by considering, say, the 3-quark, the 3-quark part, the 5-quarks being a nucleon, and then 5 quarks, they would be a nucleon and a meson found. In other words,
oh, yes, you have them that way, but why don't you... No, the question is, why is it reasonable to think of the nucleon itself as just 3 quarks? Since if the reason you don't see the quarks is because they have a mass of 20 BeV. Inside, when the 3 quarks come together to make a nucleus, they have a nucleon, they have a binding energy of 59 BeV. 3 times 20 minus 1. Okay? Now, if you have a system with 59 BeVs of binding energy around, it's very difficult to see why it should be reasonable to think of it as a system made up of 3 particles only. Okay? Why not 5? Why is it reasonable to think of the nucleon as 3 quarks rather than a mixture of 3 quarks and 4 quarks and an anti-quark, or everything else consistent with the quantum numbers? Okay, it's a highly relativistic system. We know that in a relativistic field theory, particles have certain amplitudes for having virtual pairs inside them. Aside from the question of ultraviolet divergences, these are normally small if the coupling constant is weak. But if the coupling constant is not weak, and it's certainly not weak, firstly because we're talking about hadrons, and secondly because we can't knock out the damn quarks, they must be held in there very tightly, there's no reason to believe these amplitudes should be small. So why should quark number be a good quantum number for these systems? That's a question which I will not answer in this lecture, but we have a sort of idea about an answer. I don't even want to tell you about it. It's so complicated in the first place, and it's probably wrong in the second place. But we are exploring certain ideas. Now, the people who did the naive quark model then went further. They said, well, if I can treat this as a non-relativistic system, I can use good old non-relativistic quantum mechanics, including the ideas of spin-independent forces, even though I know that's ludicrous from the viewpoint of relativistic quantum mechanics. I'll just be very bold, they said, and we'll use just very naive reasoning, including a picture of things in an attractive potential with spin-independent forces, to figure out not just the SU3 assignments of these things, but the spins. Now, they said, we'll begin with the QQ bar system, the mesons. That's sort of easy because there's no symmetry to worry about. And we'll assume the quarks have spin 1/2. That's that's the simplest assumption if we're going to get any half-integral angular momentum in. So they're SU3 triplets with nucleon number 1/3 and spin 1/2. Since this is a quark-anti-quark system, I don't have to worry about statistics. I should say the most tightly bound state will be an S wave. That's always the way it is for central potential. Of course, as previously said, from SU3 analysis, it's got to be 8 and 1 under SU3. Because it's particle and antiparticle, it has to be parity minus. And then the spins can be lined up to make either spin 1 or spin 2, or spin 0. So I have j to the p equals 1 minus or 0 minus. That is to say, I have pseudoscalar mesons or vector mesons. Of course, they don't all have the same mass, but that's the spin-orbit interaction, blah, 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 all nonsense. But on a qualitative level, it looks good. It looks like you've explained not only why the lightest bound states, the lightest bosons, are octets and singlets. You've explained why they're pseudoscalar and vector, and not scalar and pseudovector, for example. Of course, you would expect scalar and pseudovector to come up eventually. They would be p states or d states in this imagined potential. But the lightest ones should be pseudoscalar and vector. And indeed, they are pseudoscalar and vector. Looks good. Looks crazy, but by God, it's organizing the data. Okay. Shall we go on? I mean, don't ask critical questions. How can this happen or that happen? Because I don't know the answer. I'm just trying to explain what. Yes.
Well, you say that if you did it relativistically, you wouldn't get definite spins or something?
You wouldn't get definite L and S.
Oh.
You wouldn't even get definite quark number if the forces are very strong.
Mm-hmm.
It would be a mixture of a quark and an antiquark, and two quarks and two antiquarks, and.
Oh, okay.
And you know, for example, from the Dirac hydrogen atom, that the actual bound states are mixtures of different L's. A very slighted mixture, but that's because E squared is a small parameter. Okay, if E squared were a large parameter, there'd be a large admixture of different L's. It would only be the total angular momentum that would be conserved.
Okay. But you would get definite spins?
Oh, yes, because total angular momentum is good. Now, let's go on. No, I guess parity in this simple case keeps the L fixed. I take that back. But certainly there's no reason to, well, yeah, and this is when we get to the nucleons as things get stranger. Okay. Now we go to the system of 3 bound quarks, QQQ. There again, expect some sort of interaction. So the lightest bound state you would expect with all 3 quarks as close to each other as can be with no centrifugal barrier. All 3 quarks in a mutual S wave, any pair in an S wave. Space part of the wave function. Totally symmetric. This means, of course, that should be the lightest state with attractive potentials. Everything as close to each other as it could be. This means spin cross SU3 part must be totally antisymmetric because the quarks are supposed to be fermions. Now this doesn't work, and therefore the quark modelers, real madmen, every last one of them, said, well, let's try the alternative hypothesis. I don't have time to show you totally antisymmetric, doesn't work. As if the quarks were bosons. We will return to this point later. I just want to show you the fact they aren't bosons, if they exist at all. I'll show you how that difficulty is gotten rid of. But let us just work out what happens if if one assumes that the space times the spin times SU3 part of the wave function is totally symmetric. That's a nice little group theoretical exercise, whether you believe a word of this nonsense or not. This requires a small group theoretical digression on the permutation group on 3 objects, or as it is called by its friends, S3. Because we've got a 3-particle system and we've got to work out how we put together spin and isospin and SU3 wave functions to make something that is totally antisymmetric. So it will be a digression. S3 is this finite group with 6 elements, the 3 factorial permutations on 3 objects. If we only had 2 objects and we were flipping them around, then we know there would be trivial representations of the group, either symmetric, the trivial representation, or antisymmetric. With 3 objects, we can get one other representation that is called the mixed representation, and that has dimension 2. Of course, you can have a totally symmetric function of 3 variables. So there's a symmetric representation, which is, of course, irreducible, being the trivial representation. An antisymmetric representation, a totally antisymmetric function, which is also irreducible, being 1 dimension. And a so-called mixed representation with dimension 2. I don't have time to work out the theory of finite groups for those of you who didn't see it in 251 or in Glashow's course this semester, but I will try and convince you at least that there is a 2-dimensional irreducible representation of this object. Let us consider a 3-dimensional vector space with 3 coordinates labeled x, y, and z. This space forms a representation in particular of the permutation group on 3 objects, just permuting x, y, and z. There is obviously a 1-dimensional invariant subspace, not under the full group of rotations, but under the group of permutations, which is vectors proportional to the unit vector 1 over root 3 ex plus ey plus ez. That's a 1-dimensional invariant subspace of the 3-dimensional space that forms the basis for the trivial representation of the group, the symmetric one. Now let us consider all vectors orthogonal to this. That's a 2-dimensional subspace. I'll draw, it's a plane passing through the origin, but if I draw a plane passing through the origin, my graphical skill is not good enough for you to see the orientation. So I will draw a plane parallel to it, which is this plane here that intersects x, y, and z at 1. And in your mind's eye, you are to displace that section of the plane parallel to what I have drawn so that it passes through the origin. Now, in this plane, this 2-dimensional subspace, I can't reduce things any further. Because how could I have a vector in this plane that was invariant under permutations? Particularly to be variant under permutations, it has to point just as much in the x direction and the y direction as the z direction. There isn't any way to do that here because, you know, which way is it's like a Mandelstam plot. Which direction is it going to point? These 2 vectors are obviously, therefore, for this 2-dimensional subspace forms what is obviously an irreducible representation of the group. You can't break it down into 2 further 1-dimensional subspaces, and that is the mixed representation. Are there questions on this group theoretical digression? I will now tell you some facts about multiplying together and these representations, which you can work out if you wish. There are 6 products to worry about: S cross S, S cross A, S cross M, A cross A cross M, and M cross M. This is equivalent to, equivalent to, equivalent to, equivalent to, equivalent to. Well, symmetric is a trivial representation, so multiplying it by anything just gives you the same thing again. That's generally true. Antisymmetric times antisymmetric, we all know is symmetric, I hope. Antisymmetric times mixed has got to be a two-dimensional irreducible representation, and there's only one around, so it's got to be mixed. The only one you'll have to take on trust is this, which is S plus A plus M, and at least you know I'm not lying to you, because they all add up to, the dimensions add up to 4 on both the right and the left. You know it has to contain, well, you could work it out from the fact that if A cross M contains M, then M cross M must contain A. The famous permutation symmetry of Clebsch-Gordon coefficients. And therefore, this must contain S, because S cross M contains M. It must contain A, because A cross M contains M. And it's got to have something left over. That can't be an S, can't be an A. There's only one S and there's only one A, so it's got to be an M. Now, it's forced actually. Okay. Now we've got to put together 3 spins and 3 SU3 things. So the first part is the 3 spins. Well, this you, of course, know if you've done any non-relativistic quantum mechanics, like the scattering of an electron off a helium atom. In Schiff, you find these spin states worked out. By putting these two together, you can make spin 0 and 1. By adding a 1/2, you get a 1/2 from adding the 1/2 to the 0, a 1/2 from adding the 1/2 to the 1, and the 3/2. The 3/2 is a state where all the spins are aligned. So that is totally symmetric under the permutation group. The 2 1/2, as you would expect, get mixed up with each other when you permute the 3 spins. You can look at the explicit wave functions in Schiff's book if you don't believe me. And therefore, these two together form a mixed representation of the permutation group. It's the sum of 2 two-dimensional representations of the rotation group, which forms a single irreducible representation of the rotation group across the direct product of the rotation group and the permutation group. Now, 3 1/0s. 3 SU3 factors. 1/0 cross 1, or I'll just write it. 3 cross 3 cross 3 equals 1 plus 8 plus 8 plus 10. Now, what are these things like? If I think of these as vectors with one index, the 3-index tensor that transforms like a 10 is the one that is totally symmetric under permutations of the 3 indices. That's our irreducible representation 3/0, totally symmetric under lower indices. So this is guaranteed to be symmetric by construction. The singlet is what? What is the object that is SU3 invariant that has 3 indices? Epsilon ijk. What is the object that is totally antisymmetric under permutation of the 3 indices? Epsilon ijk. And these two, of course, you'll have to take it on trust again, but construct it and you'll see they get flipped among themselves. They're mixed. Now we can see what we can put together to make a totally symmetric wave function. We also see we reach total disaster if we try to make a totally antisymmetric wave function. Totally symmetric wave function. Antisymmetric, there's nothing we can put up here that will make symmetric. So this one is out from the beginning. There are no singlets. And that's right. There are no baryon singlets low-lying. You can put together a mixed and a mixed with appropriate Clebsch-Gordon coefficients to make an antisymmetric object. Therefore, we can have octet with j to the p equals 1/2 plus. It's assumed to be plus because of 3 identical particles in a totally symmetric spatial wave function. That's right. And you can put together this with this to make a decouplet that's right also. You can't make a decouplet with 1/2 plus, nor an octet with 3/2 plus. All you can make is a decouplet with 3/2 plus and an octet with 1/2 plus. Isn't that peculiar? But it looks absolutely, I mean, of course, you could make them in this model as excited states, where the spatial wave function is not totally symmetric, and one of the two quark pairs is in a p wave or something. But you'd expect that to have higher energy. But by God, does everyone understand how this is wonderful and nutty at the same time? It's wonderful because it predicts just the right spectrum. Okay? And it's nutty because it says the 3-quark wave function has to be totally symmetric. Now, this is an exciting moment, so I hope you will forgive me if I run on for 6 more minutes and tell you the answer we think we have. We means everyone. This is a universal idea. This is an idea that began as became a mad speculation and became established dogma without ever passing through the test of experiment. The idea we have for explaining these two curious facts, not the fact as to why a non-relativistic model should work well or why 3 quarks and not 5 quarks, but some other facts. Why the 3-quark wave function should be totally antisymmetric in SU3 cross spin, why there should be quark, anti-quark, and 3-quark bound states, but not quark-quark bound states, and possibly why you never see a free quark. I will just sketch it out, and then you can ask me questions at the beginning of the next lecture. So, we come to what has the elegant name of quantum chromodynamics. This is just a jokey name. That's what's new things, always something new out of Pasadena and always a joke. The idea actually came from Ken Wilson and Lenny Susskind and David Politzer here, among others. The idea is this. We're going to increase the number of quarks. We're going to give them a new quantum number. So it's not going to be 3 quarks now. There's going to be 9. And we'll see by putting in more quarks and doing things in the right way that we can solve a lot of problems. So the actual symmetry group of the strong interactions is going to be SU3 cross SU3. The quarks are going to be triplets under both of these groups. So this is for the first SU3, the one we know and love after 2 weeks of living with it, and this is for the mysterious second SU3. These are also given jokey names. This one is called color, and the 3 kinds of quarks are labeled red, white, and blue. And this one up, down, and sideways, and this one, actually a joke of Nambu's, is called flavor. That's our old friend SU3. So, but just so we don't have to say our old friend SU3, we say SU3 flavor and SU3 color. Now, the colored particles have never been seen, and that's made a hypothesis. The hypothesis is that there are very, very super strong interactions between colored particles so that the only physically observable states are color singlets. All observable states we think we know how to do this. There's still some dispute. The general idea is you treat color SU3 just as we treated electromagnetism, by making it a gauge group. That means you have 8 massless vector mesons for the 8 generators of color SU3. Now, one thing you can see, but it's not like electromagnetism in that the force is very strong. Now, one thing you can see from this, a necessary consequence of this is that color non-singlet states will be much lighter than color singlet states. Because color non-singlet states, having a non-zero color, will have non-zero values of these gauge fields at infinity. And therefore, when you add up the energy that's stored in the gauge fields outside the particle, you'll get a positive answer. Whereupon if you have a color singlet, the gauge fields vanish at infinity, and at least you don't have that positive contribution. Whether you can make them very much heavier than color singlet states, infinitely heavier, is an open question. And I am preparing a preprint at the moment on this thing in 2 dimensions, where it's an easier question to answer than in 4. The answer there is...
Observability of the 8 mesons.
What?
How about the observability of the 8 vector mesons?
They're also colored. They carry color because it's a non-abelian group.
But
Imagine if it were...
you said something about they were massless?
They were gauge mesons. That means they have 0 bare mass, but they may acquire a mass. They may... these mesons, everything has a funny name here. These mesons, I love the subject for everything except its nomenclature, which makes me feel like Bozo the Clown whenever I deliver a lecture. They're called gluons because they glue things together. And just as you can't observe free quarks because they are not color singlets, so the gluons, of course, transform according to the octet representation of the group, like its generators, and therefore you cannot observe gluons. You can observe, of course, bound states made up of gluons, just like you could observe bound states made up of quarks, and these are called glue balls, God save me. But at the moment, there is no definite meson that has been identified as a glue ball. Quarks seem to be sufficient. This is a land of mists and fogs, okay? In the next lecture, we will start talking about the dispersion relations, and we'll be back on solid ground. But this is a guided tour of the lands of mists and fogs, where castles you see in the distance may turn out to be mere fata morgana. But we should have at least one lecture like that in this course. Off the high road and into the swamps. So let's see how this solves our problem. Firstly, you cannot make a color, although of course you can make a color singlet out of quark and anti-quark, 3 cross 3 bar color. You can't make a color singlet out of 2 quarks. 3 cross 3, as I demonstrated, is 6 cross 3 bar. So we explain why there is no 2 quark bound state. And indeed no bound states of 2 quarks and an anti-quark, or 2 anti-quarks and a quark by similar computations. You just can't make a color singlet. You have 3 quarks. There are 3 triplets under color, as well as triplets under ordinary SU3. So the same equation I have written on the bottom of the right-hand board here is still valid, except this SU3 color I'm now counting, not SU3 flavor. And I can put together 2 3 triplets to make a singlet. Now it is anti-symmetric in color. And now even if they're ordinary fermions, since I have a new degree of freedom, it's forced to be anti-symmetric in color. The rule is it has to be anti-symmetric in space times spin times SU3 flavor times SU3 color, all the degrees of freedom. By our rule that it has to be a color singlet, it is forced to be anti-symmetric in color. By the ideas of the naive quark model, the space part is totally symmetric, and therefore spin times SU3 is totally symmetric also, so the whole thing should be overall totally symmetric. And we've reduced this mysterious principle to just one question mark and one exclamation point, since the rule that it has to be a color singlet is still on somewhat disputed grounds. And that is the end of the part of the lecture about quantum chromodynamics. Next lecture, the Kramers-Kronig relation and its descendants, and a trip into the bowels of Feynman diagrams, from which we will emerge only after the spring vacation. Okay. Don't forget the problem set, something to keep